Hello everyone. In this lecture, we are going to start the numerical part of the course. Um, and before moving to the understanding the finite difference method and other methods for discretizing the PDEs and to be able to solve those partial differential equations using numerical methods, I want to introduce and talk a little bit about a different type of errors that we might face when we discretize or digitize the solutions in a computer. Okay. And in this lecture in particular, we will focus on one type of error, which is Randolph error. And then after that, we will talk about truncation errors and Taylor series. And after that, we're going to drive finite difference schemes to be able to solve partial differential equations numerically. Okay, so we have different type of errors that we might face and encounter when we solve partial differential equations numerically. So the first type is what we call as Randolph errors. So these are because of their representation of numbers by computers with a finite number of digits. So we will talk more about this. This is because in computers we can only show and represent any number with a finite number of digits, right? So we cannot use an infinite digit in computers. So this will lead to what we call as Randolph errors, where we round the numbers to those significant digits. The second type of error is truncation errors. So these are because of approximation by numerical methods of exact mathematical operations. And by that I mean, like, for example, you have differentiation in the exact form, in the exact continuous space, and then you do use, for example, finite difference or any discretization method to represent that in a numerical scheme, and that approximation has some errors which we call as truncation errors. Also, we have other errors. So we have any different type of errors as well. For example, your model can have an error, right? The reduced model that you are trying to represent any physical phenomena might have some errors itself. The data that we are using can have errors. So this is called data input error. And also your code or whatever, your data, anything, all of them can have some errors that are due to your mistake, which is called human errors. Okay. So these are the possible errors that you might have when you are trying to approach a problem, especially a numerical problem. And so you have to be aware of all of them when you want to, for example, debug your code or kind of find a reason why your code or your numerical solution is not working well. Okay. So in this lecture, I'm gonna focus on these Randolph errors, which are the also called machine errors. I think this is important for you to know that how machines and computers represent numbers, and what are the errors that we might face by this representation in machines. Okay, so we have Randolph errors. So I want to define some stuff before going to some examples of this. So the first one is significant digits. Significant digits. So significant digits is like the digits that come before that you want to represent in a computer. Okay, so these significant digits, for example, this is what we call later on when I define floating points. That would be like more clear to you. But for example, say you have this number 1, 2, 3, 4. Okay, the significant digits here, because the way we are going to represent that is going to be 1. For example, 2, 3, 4 is the significant digits, and are significant digits, and these are the ones that we are gonna focus on, and the rest we can show by like exponents and other stuff. And for example, if you have more than that, for example 5, 6, because your significant digits is like 4, your mantissa, which I'm going to talk about, that is 4, then you are not going to show those numbers. Okay, so the omission of significant digits, this is one of the reasons of the Randolph errors, that is omission of significant digits in computers lead to Randolph errors. Okay, like if you omit some of those 56, for example, here, if you have more and then your significant digits are 4 numbers, 4 digits, then omitting these will lead to the Randolph error that we were talking. Okay, so the other important thing in computers are number systems. So as you know, in most of our applications, we use a decimal point or base 10. Base 10 to represent numbers. For example, 1, 2, 3, 4 in base 10, 1234 is 1 times 10 to power 3 plus 2 times 10 to power 2 plus 3 times 10 plus 4 times 10 to power 0, right? But computer, as you know, it's used as 0 to 1, right? It's binary system. So it's base 2. The numbers are base 2. And so, for example, 1101 in base 2 is going to be 1 times 2 to the power 3 plus 1 times 2 to power 2 plus 0 times 2 to power 1 plus 1 times 2 to power 0, which is gonna be, if you add all of these, will be 13 in base 10. Okay, so this is base 2, which is usually used in computers, and this is important for you to know. Okay, and so the other thing I want to talk is, so we talked about these Randolph errors. We're going to talk more and these number systems. And the other thing I want to talk is now the representation of numbers in computers. Okay, so let's see the first one. The first one is we want to talk about integer representation. So the integer numbers, how they are represented in computers. So integer representation in computers. So usually for integers, we say that first bit, which is a 0 or 1, right? Because this is a binary system in computers, is gonna be the sign, and remaining bits are used to store the number. So for example, for a 16-bit computer, let me do it in the next page. So for a 16-bit computer, so 13 in base 10 is gonna be represented like this if you have 16-bit. Okay, so the first bit is gonna be minus, let's say minus 13. So the first bit is gonna be the sign. So if it is positive, it's gonna be 0. If it is negative, it's gonna be 1. So because this is negative, I'm gonna just put 1. And then the rest, and if you remember, this is 13, right? We have already found it in base 2. So this is gonna be then because we have the rest should be represented number. So it's gonna be, because we have 16 bits, we have to go, we have 4 bits here for this, and then 1 for the sign, so it's gonna be 5. So I have to go 11 bits. So 11 bits 0, so it's gonna be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so 11 plus 1 is 12, and then we have 1, 1, 0, 1. Okay, so this is how an integer is represented in a computer. So let me just say, this is because we have negative sign, and this shows the sign of the number, and this is 13 in base 2. Okay, so this is how we represent an integer in computer. Okay, so let's say I want to find the largest range of numbers integer numbers for a 16-bit computer. So it's gonna be, as you see, we have 15. We can have 15 bits just to represent numbers because this is 16. So I'm gonna have 2 to the power 15 and minus 1, and the reason is 0 is gonna be both for positive and negative. So this is, we are gonna have from minus 32,768 to 32,767 if you calculate that. Okay, so it's gonna be from 0 to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 15, yeah, right. Oops. Okay, so this is how much we can represent the number, and this is for integer representation in computer. So it's pretty straightforward that how we can represent integers in computers. And now I want to talk about floating number representations, which might be a little bit trickier than that. So floating number representation. Okay. So for floating numbers, we typically convert them into this. So if you have a floating number, and this is also sometimes called a scientific convention. So we say first is going to be the sign of that. So I'm going to write it as -1 to power sign. And then I'm going to write it as a mantissa, which I'm going to talk what it is, times a base. For example, the base could be 210 to an exponent. Okay, so I'm going to represent any floating number as this way. Okay. And I'm going to show it with computer in this manner that I'm going to talk about. So let's say we have this. If these are our bits, so we are going to have 3, 1 here. The first one is going to be for the sign. Second one is going to be for the sign of the exponent. Third one is going to be for the exponent, and fourth one is going to be for mantissa. So let me talk about them. So this is going to be for the sign, or S. This is going to be for, and I'm going to show it down here. It's going to be for a sign of exponent. This is going to be for exponent. And the last part is going to be for mantissa. Okay, so let's see what it is. So M, actually, let me just write here, from here, is mantissa, or fractional part. of a floating number. B is going to be the base, and E is exponent. Okay, so let's see an example. So example, so for a decimal base, so let's see how we are going to represent this in computer if we were to represent it. So 0.00789. So we are gonna represent. No, this is the general procedure, and then we are in the computers. We only use this for base 2, which is binary. Okay. So I just want to say this representation, this general representation, which is also called kind of scientific representation of floating numbers. So we are gonna represent this as 0.7889 to in base 10 times 10 to the power minus 3 base 10. So depending on the convention, sometimes they also show it, you might see in some books that they show this with 7, 8, 9, 10 times 10 to the minus 2, okay? And in binary system where the base is 2 and is used for computers. So for example, we have 1.0.01 in base 2. We are going to show this as 0.1001 in base 2 times 2 to 2 in base 10. Which is gonna be 0.1001 in base 2 times 2 to power 1, 0 in base 2. Okay. Again, sometimes they might show it in as like 1.001 times 10 times 2 to 1 in base 2. Okay, so this is representation, and here I'm going to use this way of representing that, or this way of scientific representation. So mantissa, or M, should be normalized such that no number greater than 1 on the left exist. Okay, so for example, 0.0058 is gonna be 0.588 times 10 to the minus 2. This is this representation that we were seeking. And 580 is gonna be 0.58 times 10 to the power 3. Okay. So in decimal numbers, this is our convention. M should be between 0.1 and 1. And in binary numbers, this should be in 0.1 in base 2, which is going to be 0.5 in base 10, and 1. So it's going to be between 0.1 in base 2 and 1. And in general, for any base, M should be between b to the power minus 1 and b to the power 0. Okay, so this is the mantissa, how the mantissa should be. The range of mantissa.